today we are going to prepare the biological buffer, and the principle, what is exactly the principle of this biological buffer system. Buffer may be a mixture of weak acid and its conjugate base, or weak base and its conjugate acid. They resist changes in pH upon addition of small amount of strong acid or bases. In physiological system, this property is vital for the maintenance of homeostasis. For example, most of the body fluids contain natural buffering system such as blood buffer system, saliva buffer system, urine buffer system, mucous buffer system, and etc. As if you see that little bit, I brief what is pH. The pH is a unit of measures which describes the degree of acidity or alkalinity, or otherwise called acid and base of the solution. It measured on the scale of 0 to 14, and the formal definition of the pH is the negative logarithmic of hydrogen ion concentration or hydrogen ion activity is considered as a pH. The pH value of substance is directly related to the ratio of hydrogen ion concentration or hydroxyl ion concentration. The H plus ion concentration is higher than hydroxyl ion, it may be considered as acidic, or if the hydroxyl ion concentration is higher than H plus ion concentration, it may be considered as a basic. 7 is considered as a neutral, and less than 7 acidic, and greater than 7 basic. And if you see that the Bronsted-Lowry, the definition for acid and base, Bronsted-Lowry acid can be considered as a donating of H plus ion or acid, or Bronsted-Lowry base if you want to refer, which can accept H plus ion or which can donate hydroxyl ion. That's why we call it as Bronsted-Lowry acid and Lowry base. And if you see that Anderson-Assenberg equation will describe about the pH, and the acid dissociation constant is as follows: HA derived as a dissociation into H plus ion and hydroxyl ion. If you take as a water here example, H plus ion plus OH minus ion. So the constant, dissociation constant for the water, you can substitute here. The total, the H plus ion plus hydroxyl ion concentration will give rise to the total of water molecule. So for any acid, HA, the relationship between that ionization constant, the concentration existing at equilibrium, and the solution pH is given by pH equal to that ionization constant plus log base 10, and hydroxyl ion concentration, if you are taking water as an example, divided by H2O, or H and A. This is both male and female of H plus and OH minus ion concentration. So the buffer, if you see that what is buffer? The buffer or solution that resists changes in the pH on the addition of acid or base. Most buffer consists of a weak acid and its conjugate base, or most of the buffers can consist of weak base or and its conjugate acid. And if you see that the figure here, how the plot of the pH versus the base added is flat near the ionization constant pKa. Buffers can only be used reliably within a pH unit based on their ionization constant. So inside, if you take that the human being, that the biological buffer system, you see that in our body, you have the two different buffer systems we have in our body: extracellular fluid and intracellular fluid. Extracellular fluid, which include the carbonic acid and bicarbonate buffer system, is the best example which is present in the blood. And if you see that the protein buffer system in the blood as well, in the plasma, we'll discuss later, that the plasma protein also can be considered as an extracellular buffer system we have in our body, that the protein. And if you see that the intracellular fluid, there are two different buffer systems. You have phosphate buffer system and protein buffer system. The protein buffer system, you have the hemoglobin. The hemoglobin is nothing but the protein, the 4-5 ring, which can be coordinated with the iron, and that buffer system also that works RBC only. Amino acid buffer system also, if you see that the peculiar character of amino acid, it can become the deuterion or dipole in nature. Because of that, the amino acid can be used as a buffer very nicely in works inside our buffer system. These are all the three buffer system mainly works in our body to maintain homeostasis of any biological reactions to convert, whether it may be a carbohydrate metabolism or protein metabolism or nucleic acid metabolism or lipid metabolism. Any kind of metabolism will takes place because of this three different biological system which works perfectly, or else it's a failure of metabolism and it leads to physiological problem of the system. So, what are the biological buffers? The biological buffers can be considered as a general criteria such as the pKa should reside between pH 6 to 8. They should exhibit high water solubility and minimal solubility in organic solvents such as methanol, ethanol, etc. And they should not permeate cell membrane. They should not exhibit any toxicity towards the cells, and they should not interfere with any biological process. The salt, minimal effect of the salt which we are using to prepare the buffer here. So, ionic composition of the medium and temperature should have minimal effect of buffering capacity, and buffers should be stable and resist to enzymatic degradation, and buffer should not absorb either in the visible or UV region of the photoradiations. If you see that the carbonate and bicarbonate buffer system works very well in the blood system to maintain the lung air space works, and approximate pH and bicarbonate concentration in the extracellular fluid, especially in the blood, how exactly it the range, the fluid, if you take the plasma, the pH should range between the 7.35 to 7.45. The bicarbonate ion milliequivalent should be 28 milliequivalents bicarbonate ion per liter, and cerebrospinal fluid, CSF fluid of main vertebra, if you take that fluid, the pH should be 7.4, and the bicarbonate ion concentration should be 25 milliequivalents per liter of cerebrospinal fluid. And saliva, if you see that the saliva pH is 6.5 to 7.4, and bicarbonate ion concentration should be 10 to 20 milliequivalents per liter. Gastric secretion, the pH 1 to 2, and it doesn't have any bicarbonate ions, 0. Tears, the pH 7 to 7.4, the bicarbonate ion concentration milliequivalents is 5 to 25 per liter, and aqueous humors 7.4 pH and 28 milliequivalents of bicarbonate ion per liter of aqueous humor solution. Pancreatic juice, pH 7 to 8 and milliequivalents per liter of pancreatic juice is 80, and sweat pH is 4.5 to 7.5. The milliequivalents of bicarbonate per liter of sweat is 0 to 10. So one by one we have taken the 5 different buffer system. For example, if any buffer system, if you want to prepare, first we have adopted that the reference of this particular buffer, anything, the biological standard buffer system which was published in 1969 in Methods in Microbiology Volume 1, first edition by Norrish and Ribbons. They are the pioneer. If you want to work with any biological system, or if you want to work with any biomolecules to study about the structure and functions and enzymatic activity, to cell-free extract preparation or fluid preparation or working with any fluid, you need to provide a particular proper environmental condition as it is existed in the native form. That simulation should be given. That's why the biological buffer system is very important. So the first, the secret buffer, if you want to prepare the secret buffer, the pH ranges from 3 to 6.2 according to the pKa, ionization constant of this pKa of secret buffer can work perfectly with between 3 to 6.2. If it is less than 3 or more than 6.2, the secret buffer should not be used because it leads beyond that ionization constant. It cannot work as a buffer. It may be work as an acid, or it may be work as a, if it goes beyond to 6.2 is alkali. So between the 3 to 6.2 pH range, only this secret buffer can be used as per the Methods in Microbiology Volume 1, the people published in 1969. So if you want to prepare any buffer system, either you have to use a weak acid and its conjugate base, or a base and its conjugate, weak base and its conjugate acid. So vice versa. So here, if you want to prepare prepare one acid and one base should require to act as a buffer system. And the citrate buffer, if you want to prepare, first you have to make the stock solution A and stock solution B. Stock solution A, the 0.1 molar citric acid and 0.1 molar, if you want to measure, just see that the molecular weight of citric acid and convert it into 0.1 molar citric acid for 1 liter. Suppose if you want to measure, if you want that the 100 ml, according to that you can vary the volume, and then 0.1 molar solution of sodium citrate acid and its conjugate base is 0.1 molar, it's 29.41 gram of sodium citrate can be taken and dissolves in 1 liter. From this 1 liter and 1 liter stock solution, you want to prepare pH 5.5. As you can see that the tabular column as given by Methods in Microbiology Volume 1 published by the Nourish and Ribbons, that the 5.4, the pH 5.4 that can be equal to 5.5 you can consider, and you have to take the solution from citric acid 34 ml from that stock solution, and then citric acid should be taken from 16 ml and mixed together and make up. If you are making up that 16 ml of citric acid solution into 100 ml standard flask, and to this add exactly 34 ml of sodium citrate solution and make up to 100 ml, then it will give rise to 0.1 molar citric acid sodium citrate buffer pH 5. Suppose no need to check the pH here. If your chemical and your measurement is perfect and the water which you have used is very perfect, then you have measured this and put it into 100 ml and make up to 100 ml, and if you check the pH, exactly it shows pH 5.4 to pH 5.5. So this is the first buffer, and the second carbonate bicarbonate buffer pH 10. Here the two different stock solutions